Good morning. So this is B. Venkateshwar Rao, working as Senior Assistant Professor of EC Department. Just I want to discuss about the electronic devices and circuit of a 7th unit, which is titled as Field Effect Transistor Amplifier, FET amplifiers. Okay. First we'll see, we already know that a field effect transistor which has 3 terminals, as we have seen in case of bipolar junction transistors, whereas it has a drain, source and gate. So each and every field effect transistor, it has been classified into 3 types of configurations. It has 3 terminals of field effect transistor, has a common source configurations, common gate configurations, common drain configuration, where if the gate is made as common between the drain and source, it has been called as a common gate. Similarly, common source is nothing but where the source terminal has been made common with the gate and drain terminals, so that it has been given as the name common source. In a similar fashion, the common drain, where the drain terminal has been made common between the gate and source, so that it has been given common drain amplifiers. So first we'll see the 3 configurations, in which each and every configuration during amplification it will be acting like as an amplifier. So further it has been given in different types of biasing techniques. So first biasing technique we are going to discuss regarding the common source amplifier. So where it has been given as field effect transistor common source amplifier by biasing technique, the fixed biasing technique. So this circuit which is shown over here, it represents the biasing technique of a fixed bias for the case of common source amplifier. So where the arrow mark which represents over here, it represents an N-channel JFET. So it has been given for the N-channel model for the field effect transistor, where it has 3 terminals, just now have said as a gate, drain and source are these 3 terminals, where it has been given very input resistance which is connected over here is a gate resistance, in the similar fashion drain resistances, where it has been given in a further a voltage supply of VGG towards the gate to maintain. It has been given a negative, so it should be maintained as a reverse bias here, and separate in the input voltage it has been biased over here, and the capacitance given over there C1 and C2 it provides so to blocks the DCs, as it will be used to amplify the AC signals. So the function of the capacitors, as we know that the capacitors which are connected at the input and output, it used for biasing the circuit, and as well as it blocks the DC signal, so that we can get a pure AC signals. So it's a circuit which has been shown over here. So to analyze this circuit, so we can analyze this circuit by making use of the low frequency equivalent circuit. The same circuit whatever it has been given over here, so we can get an equivalent circuit for this circuit diagram by short circuiting the capacitances. Okay, so that has been shown over here, where it gives a low frequency equivalent model where the capacitors have been totally short circuited over here. So where it has been given the same, whatever the input impedance Zi, it has been given as an input impedance, as it has been shown over an input impedance. The same fashion it's an output impedance, so it has been an output impedance, and the internal whatever the circuit it has been given the symbolic, so that has given as an equivalent diagram by replacing the source and voltage terminals over here. So this gives the total, so the same, it's a gate, it's a source and it's a drain. So with the help of these equivalent model, so we can analyze this circuit by deriving some of the parameters. So we have some important parameters we are going to derive in each and every configurations, that is so input impedance, output impedance and voltage gain. Each and every configuration has the similar fashions of derivations. So now we are going to discuss about the fixed bias technique. Now just we'll derive the respective derivations regarding this common source field effect transistor with fixed bias. As we have seen in the earlier case, we have drawn a circuit diagram. With respect to the circuit diagram, we have drawn the equivalent circuit diagram just by short circuiting the capacitances with the low frequency effect. Okay, now we'll see some of the parameters how we are going to derive based upon the equivalent circuit which you have drawn there. So first coming to the input impedance. So the input impedance represented by Zi, as we'll be looking from input side of the circuit what we have drawn in the equivalent case. So it is directly looking only the one of the resistance which is connected to the gate terminal will be of an input impedance. So it is available. So that gate resistance will be the input impedance for the case of the common source amplifier. Next coming to the output impedance. So now to calculate the output impedance, we have to look it from the output side of the circuit of an equivalent case. Now by seeing that, so obviously the input voltage will be of 0 as we are looking from output side of the equivalent circuit. As Vi will be equal to 0, this VGS is nothing but the voltage which is connected between the gate and source terminal. As Vi it has been 0, obviously this VGS will be also equal to 0. So by this, hence this GM and VGS will be also equal to 0. So totally the input voltage sources will be equal to 0 as we are looking from output of the equivalent circuit to calculate the output impedance. Then it is an equivalent circuit which is given from the output side by looking from the output side of the circuit. So Z0, it is looking only two resistance are available right now, as GM and VGS will be equal to 0 as we have seen in this case. So hence the output impedance can be calculated with respect to these two resistances, as these two are parallel with each other, RD and this RD. So the parallel of these two resistances will give the output impedance. If suppose if RD is very much large then compared to the RD, then totally the output impedance will be equal to only RD. So this is the calculation of input and output impedances. Next we will shift to the another parameter, that is a voltage gain, which is given represented as A suffix V. So the output voltage is the ratio of output voltage to the input voltage. The voltage gain is the ratio of output voltage to the input voltage. As we know that in case of common source amplifier, the output voltage is VDS. It is the voltage between the drain and source. Similarly, input voltage is the voltage between the gate and source. The ratio of these two gives the voltage gain. Now we will see how to calculate this voltage gain. Coming to the V0, to calculate the output voltage of the circuit, just applying the loop equation for the output circuit, we will get V0 is equal to minus GM VGS and into RD parallel with the RD. So this gives the output voltage. Now as we have seen that Vi will be equal to whatever the input voltage we are applying to the circuit, so that is the voltage between the gate and source. So Vi is equal to VGS. Then V0 will be equal to GM. Just I am replacing in terms of VGS, I am replacing by Vi. Then minus GM. So VGS it is replaced by Vi. Then this is as it is RD parallel with the RD. Then substituting the value of V0 in this expression, then we'll get AV is equal to V0 by Vi. So this V0, if I replace over here, it is GM into Vi. So this Vi and Vi will be cancelled out. So we will be remaining only minus GM RD parallel with the RD. So in some cases, if RD it has a higher value than compared to this RD, then AV will be remaining only with of minus GM RD. This minus negative sign indicates that there is some phase difference between the input circuit to the output circuit. So it is exactly out of phase. The input circuit and output circuit will be out of phase with each other. So this is how we can calculate the voltage gain. As we have seen earlier case, the FET with fixed bias. Now we are going to discuss with the FET with a self bias. Now what will be the difference between the earlier biasing and this biasing technique? So it's a second biasing technique we are going to discuss for the case of common source amplifiers, where we have, if you could see here, for the earlier case, for the fixed bias case, it has been given by a separate voltage VGG, but so that the voltage is not present here. So where we will be using that VGG, which provides a fixed biasing technique. So it provides a fixed voltage to the circuit. Hence it is also named as fixed biasing technique there. It's one of the difference compared to the fixed bias and the self bias. And one more, it's a source capacitance which is added parallel with that of the source resistance. So everything remains it's same as that of the fixed bias. Now the circuit which gives an N channel JFET for the case of a self bias. Now here the biasing technique, so applied is a self bias where it biases self by itself without giving any voltage here. It biases by itself, so that it has been given the name as self bias technique, biasing technique, where this in the similar fashion whatever be the capacitance used over here, so it provides to pass allow only the AC signals. As we are going to amplify the AC signals, the function of capacitor, it blocks DC and allows AC, so that we are allowing only the AC signals here. So and this presence of this gives it is called a bypass capacitor. Even its functions also same, it allows an AC here. Suppose if there is in the absence of this capacitance, it may load the output circuit may get loaded, or it may affect the voltage gains. To avoid that effects, we are going to add a source capacitance parallel with that of the source resistance. And in the similar fashion, whatever we have seen in case of fixed bias, the same rules we are applying over here to draw the equivalent circuit, low frequency equivalent model circuit for the case of self bias, just by short circuiting the capacitances. Here we don't have any capacitance here. Just by short circuiting the capacitance, we can draw the equivalent circuit for the case of self bias. The same, it has a gate terminal, drain terminal and source terminal over here, and it is an RG, it's an input resistance over here, and it's an output resistance, drain resistance, where we are looking inside to calculate the input impedance, and we are looking outside, from the outside, to calculate the output impedance. And it's given the internal representation converting the equivalent model for this type of symbol. Okay, now we will see the same parameters we are going to derive even in this case of a self bias, the input impedance, output impedance and voltage gain. We'll see what are the difference we are going to occur comparison with that of the fixed bias parameters and that of the self bias parameters. So if you compare the equivalent circuit what we have drawn for the fixed bias and as that of the self bias, almost those two circuits are similar. So as those two equivalent circuit diagrams are similar to that, so that the parameters whatever we have obtained in case of fixed bias, the same parameter values will be obtained for the self bias also. So same to calculate the input impedance here, as if you look from the input of the circuit, it will be total, the input impedance will be only due to the gate resistance. So that is Zi will be equal to gate resistance. Now second one, the output impedance, as the same, if we look from the output of the circuit of an equivalent circuit, obviously the input voltage Vi will be equal to 0, and hence VGS, the input voltage between the gate and source, will be also equal to 0. So because of which we will get only the output impedance only due to the resistances RD and RD. As those two are parallel, so the total output impedance will be equal to RD parallel with that of the RD. So if RD is very much greater than this capital RD, then the output impedance will be only due to the RD. Okay, that is a drain resistance. Now similarly to calculate the voltage gain, the ratio of output voltage to the input voltage, where the same is of minus GM, so into this RD into RD is parallel with that of the RD. If the RD is once again it's very much greater, it is only due to the RD we will get. So even this minus indicates there is a phase shift. So there is an input circuit is out of phase with that of the output circuit. See everything, the parameter whatever we are derived here, so the same parameters values for the case of fixed bias also. As we have seen in the first case of common source amplifier, the two biasing techniques, the fixed bias and the self bias, where we have seen the fixed bias, the circuit followed by an equivalent circuit, then we have derived the parameters of input impedance, output impedance and voltage gain. Similar fashion, we have seen the self biasing technique of a circuit followed by an equivalent circuit, then the same parameters for the input impedance, output impedance and voltage gain. So next we will shift to the second type, the common drain amplifier, where the drain is made common between the input and output circuits, hence the given the name as the common drain amplifier. So the circuit whichever shown over here, so it is called as a common drain amplifier. You see the drain is maintained common here, so where we are taking an output across the source by giving the drain terminal towards the ground, then automatically, so this the circuit diagram represents a common drain amplifier circuit, where we have a same capacitors which shows the same effect as we have discussed in earlier case, and it has a voltage separate the two voltages VG and VGS. So this VG is a voltage which is measured across the gate and the ground terminal, and whereas the VGS is a voltage which is measured between the gate and source terminal. So this voltage is different from this voltage. Now, so the output as we have taken from the source terminal here, the voltage across the source terminal, it gives a source voltage. Vs is a source voltage and Vg is a gate voltage. VGS is a voltage between the gate and source terminal over here. Now, see, as this Vs voltage, output voltage, the source voltage will be equal to sum of these two voltages, Vg and VGS. Now, as see here, whatever be the input voltage, if you apply, if you want to get an voltage of Vs, so if we vary the source voltage by varying the input voltage, so whatever be the variation which we are going to apply as an input voltage to the circuit, the same variation which is obtained in a Vs, because see, as Vs is equal to sum of these two voltages, as Vgs will be remaining constant throughout the case. Vgs will be constant as the voltage between the gate and source remains constant always, and only Vg varies. As input varies, Vg also varies. So as this remains constant, whatever be the extent input varies, the same extent Vg varies. Hence, so indirectly we can say that Vs is depending on this Vg further Vi. So internally, as Vs can be obtained by variation in the Vi, as the source voltage totally depends upon the variation of input voltage. Hence, it has been named as source follower. So this voltage, source voltage, as Vi varies, Vg also varies, it is remains constant. So as Vi varies, Vg varies. So this source voltage also varying. So that it is called as a source follower. Now, in the similar fashion, what we have seen in the, to draw the equivalent circuit diagram, short circuiting the capacitors. Thus, short circuiting the capacitors, we have seen the equivalent circuit of a common drain amplifier, where it has been given as a gate drain. See here, the drain terminal has been grounded over here, whereas the output is collected from the source and gate over here. So that it has been named as common drain amplifier. It is a complicated one to analyze to get the parameters to derive it. Hence, it has been most simplified in the another fashion, and it has been given as the same is a gate resistance, and followed by the same concept what we have seen there. It's a drain current, it's a source terminal, gate terminal, drain terminal. Now drain is common between the gate and source. It is a common drain where the output is in a V0, where we can calculate the output impedance in the similar fashion by seeing from the output of the equivalent circuit and we can calculate the input impedance by seeing from the input of the equivalent circuits. Now we'll see how to derive the parameters for input impedance, output impedance, and the voltage gain, as we have seen the earlier case. See, as we have discussed the parameters regarding the common source amplifier, in the similar fashion, just we'll see the parameters of common drain amplifier. So first let us see the input impedance. So Zi is an input impedance. So when we look from the input of the equivalent circuit, so we'll look only the gate resistance across that circuit. So the total impedance of the equivalent circuit will be equal to the gate resistance. So Zi is equal to Rz. So next, coming to the output impedance. So if we see from the output equivalent circuit, then there are two types of resistances which are which we can see here, where Z0 dash is across the RD, small RD, and Z0 is across RS. Now total, to calculate the output impedance, there RD is parallel with the RS, where RD is seen, the Z0 dash is an impedance measured across the small RD. So those two are parallel. First we are going to calculate about the Z0 dash. Later on we are substituting in it to get the total output impedance. So to calculate the impedance here across the drain RD, then it will be equal to the V0 by ID, output voltage by an output current. Output voltage is V0 and output current is a drain current, where the obviously input voltage will be 0 as we look from outside. So then from applying KVL to the outer loop, we'll get the sum of the equation as Vi plus VGS minus V0. The total output voltage will be equal to sum of these two voltages. So as Vi will be equal to 0, if we look from the outside, so Vi will be equal to 0. Substituting Vi equal to 0, we'll get VGS will be equal to V0. Now from the figure we get ID equal to Gm VGS. So whatever the current source we get from the output of the circuit, so that is Gm VGS, so that is nothing but the drain current. As we have VGS equal to V0, so just replacing the value of VGS with the help of V0, then the drain current reduces to ID is equal to Gm V0, bringing back this V0 to ID. Then ID by V0 will be equal to Gm. So as Z0 dash will be equal to V0 by ID, so Z0 dash will be equal to 1 by Gm. ID by V0 is Gm. Now we have to calculate V0 by ID, then it will be equal to 1 by Gm. So this is the value of the impedance obtained across the small RD. Then substituting the value of Z0 dash to get a total output impedance. So this 1 by Gm is parallel with the RS. So this gives the total output impedance of the common drain amplifier. So this is what we can calculate the output impedance by seeing only from the output of the circuit. Next, coming to the third parameter, that is the voltage gain. So AV. So it's obviously it's the ratio of output voltage to the input voltage. Now from the figure we can write the output voltage will be equal to minus. If you write in a loop equation, it will be of negative the direction of current, so that because of this minus have come over here, so minus ID, RD is in parallel with the RS. As we know that ID is equal to Gm VGS, just substituting the value of Gm VGS in place of ID, then we get V0 is equal to minus, so ID in place of that we are writing Gm VGS, then RD parallel with the RS in the same. So then as we know that from the equation 1 here, so Vi plus VGS minus V0 equal to 0, I am using the same expression here where Vi will be equal to minus VGS plus V0. So this minus VG0 remains same, whatever the V0 we have got, so that it has been substituted in this equation. Then after simplifying this, we'll get the value of Vi separately and V0 separately, but we want the voltage gain, which is the ratio of output voltage to the input voltage. Now AV, the voltage gain will be equal to, this is the expression of output voltage ratio of the input voltage. It is in a Vi, it is in a V0, ratio of V0 by Vi. So this gives the voltage gain. Now as VGS can be cancelled out, negative can be cancelled out, then the leftover terms are, it has been written here. So that voltage gain will be equal to Gm into RD parallel with the RS by 1 plus Gm into RD plus parallel with the RS here. Now if RD is very much greater than RS, so this term will be neglected here, then left out the voltage gain will be having only the terms Gm RS by 1 plus Gm RS. So this is a final expression of V0. So this is how we can calculate the three parameters regarding the common drain amplifiers. See, we have seen that how the FET amplifier will be used in a common source and common drain amplifiers. Next, let us shift to the generalization of field effect transistors. The generalized field effect amplifiers is nothing but there are three different sources are connected to the three different terminals. We have the three terminals, the drain, source and gate. Whatever be the three terminals it has, the sources will be given in series connected to that of the terminals. You can see here where the gate is connected by a voltage source, that is called an input voltage, and whereas the drain is connected by a voltage source VA here, another voltage source is connected with the source, that is a VS. There are three terminals is being connected by three different voltage sources in series. So this type of arrangement of field effect transistors, it has been called as a generalized field effect transistors. So we can analyze these in three different ways, as that of the common source, common gate and common drain amplifiers. So to know the simplification of this, so we have to once again draw the equivalent circuit for the respective generalized field effect transistor amplifier, where it has an input voltages. See, so there will be two input voltages and one will be output voltage source over here. To draw the it's an equivalent input circuit diagram for this circuit diagram. Similarly, so it is an output equivalent circuit. So when we look into the drain, it has been given as when we look into the drain, so this will be the equivalent circuit with respect to whatever be the factors represented over here, and if you look into the source over here, this will be the equivalent circuit for the respective generalized field effect transistor. Now the options, the term mu and mu plus 1 terms are separately introduced over here. So where the input voltages will be multiplied with that of the mu times, minus mu times, where the supply voltage it has been reversed over here. So it has been generalized by multiplication of this input voltage by minus mu times, and whereas for the case of sources it has been multiplied by 1 plus mu times. So that it has been specially it has been given here to simplify this field effect transistor by the generalization methods to get the parameters. The same it has been given in case of output circuit diagram also. Now we will see what are the factors of short circuited, what will be the value of voltages with this respect to generalized field effect transistor when it has been analyzed in three different ways. As we know that the first case when the source terminal is maintained common for this circuit, then it is called a common source amplifier. When the source is common, obviously the source Vs and Va will be equal to 0. This Vs and Va will be, these two voltages will be equal to 0 when it has the source has been made common with for this circuit here. Then input voltage will be Vi, then output will be taken across V01, as Vs will be equal to 0, obviously there will be no voltage across V02. So for the case of common source amplifier, these two voltages will be 0 and input voltage is Vi, we are collecting the output at V01. So this is how we can calculate the voltages for the case of common source amplifier. In a similar fashion, for the case of common gate amplifier, the voltages Vi and Va will be equal to 0. So this Vi and Va will be equal to 0 when the gate terminal has been made common for both the input and output connections of the circuit, where now the Vs will be then an input supply here and the output is taken across V02. As this will be equal to 0, anyhow this will be equal to 0 over here, as these two voltages are maintained 0 and the input is given across Vs and the output is collected at V02. So this is how we can calculate the value of the voltages and input and output voltages when the gate terminal has been made common. The one more type is a common drain amplifier. As I have said, it is also called as a source follower, as the source is following the input. Whatever be the changes occurs in the input will follow the same for the case of voltage sources, so that it has been called as a source follower. For the case of common drain, this drain RD will be equal to 0 and the same Vs and Va will be equal to 0. This Vs and Va will be equal to 0, as we have seen in case of common source. In case of common drain also, these two will be equal to 0. Only the difference is that the input here it is an a Vi, even it is an a Va. The output will be different, as we have taken as a output V01 in this case, whereas for the common drain case, the output is collected across V02. Only the difference is that Vi is an input, V0 output is taken for the case of common source, and Vi is an input and output is taken across V02 for the case of common drain. Only the difference we have between these two. Now we will see how to calculate the output impedance and the voltage gains for all these three factors with the help of the equivalent circuit diagram. Now we will calculate some of the parameters for the case of generalized field effect transistors whenever the three different types of voltage is applied to the three different terminals. So first, coming to the common source amplifier, whenever the source is common, then we have seen the conditions that where Vs will be and Va will be equal to 0. When these two will be equal to 0, the input voltage is Vi and output voltage is V01. Then to calculate the voltage gain, we have to take the ratio of output voltage to the input voltage, where V01 is an output and Vi is an input voltage. Now from the equivalent circuit which we have seen drawn earlier case, so from that the output voltage which is obtained here can be given by the expression mu times. I have told that it has been multiplied by minus mu times, so that output voltage will be equal to minus mu into Rd, and whereas input voltage will be equal to the total this value here. Then the ratio of those two gives the voltage gain, where mu can be replaced by a GMRD. So mu is equal to GMRD, and same it has been represented as, in case of mu also we can represent into GMRD over here. Now to get in a simplified form, it has been multiplied and divided by Rd. So just multiplying and dividing this expression by Rd to get in a simplified form, the voltage gain will be obtained as a minus GMRD by 1 plus GMRS plus Rs plus Rd by Rd. So it is an expression which is obtained for voltage gain whenever the sources Vs and Va is maintained as 0 for the case of common source amplifier. Next, similar fashion we can calculate the output resistance by using this expression as when these two voltages are equal to 0, when the input is applied to the Vi and output is collected at V01, then whatever be the output impedance or output resistance is obtained. So for the case of common source amplifier is obtained by this expression. So these are the parameters regarding the common source amplifier. Next, coming to the common gate amplifier, whenever the gate is maintained common, we have seen the sources of input Vi and Va will be equal to 0. When these two will be equal to 0, the input is now Vs and the output is collected across V01. So obviously the ratio of output voltage to the input voltage is an voltage gain. Now it will be of 1 plus mu times. It has been multiplied by 1 plus mu times here, 1 plus mu into Rd, and this remains the same as that of the earlier case we have seen. Only thus the difference we have in a 1 plus mu here and whereas in a minus mu. So now, when it has been once again replaced by mu is equal to GMRD here and mu is equal to GMRD, the same it has been represented by replacing mu is equal to GMRD, and now same to get in a simplified form, once again it has been multiplied and divided by 1 by Rd, and this is in a simplified form of a voltage gain for the case of common gate amplifier. And similarly the output resistance expression is obtained from the resistances which has been parallel R0 and Rd. So it's in a final simplified expression for the output resistance for the case of common gate amplifier. Next, coming to the last one, the common drain amplifier. For the case of common drain amplifier, it is also called as a source follower, where for this case this Vs and Va will be equal to 0 with the help of the Rd will be also equal to 0 simultaneously. With these conditions we can calculate the voltage gain for the case of common drain amplifier, where the output will be now V02. The output is taken across V02 and the input is Vi. Just substituting the value of V02 here, it's a mu Rs by 1 plus mu, and its Vi will be Rd by 1 plus mu Rs. But taking simplified this, taking to the numerator and taking to the denominator, we can get the simplified form of this expression. Now once again substituting mu equal to GMRD, so it's we get once again replaced by mu will be equal to GMRD. To get in a simplified form, once again it has been multiplied and divided by 1 by Rd, so it is the final value of the voltage gain. So as Rd is greater than Rs, then the Rd will be neglected, then it remains only in terms of Gm and Rs. So it's how we can calculate the voltage gain. So for the case of common drain amplifier, where the output resistance also is in a similar fashion, R0 is equal to Rd by 1 plus mu, and mu is replaced 1 by GMRD. To get in a simplified form, once again it has been multiplied and divided by 1 by Rd, then the simplified form of an output resistance, it has been given as 1 by Gm plus 1 by Rd is in a simplified form. So in this way, so if we remember the whatever be the voltage source are 0 for the respective configurations, either common drain, common gate and common source, so we can easily obtain the parameters for the voltage gain and output resistances by multiplying the factors of minus mu and 1 plus mu. It's very easy to analyze these parameters.